An isotropic aluminum bar in the figure is loaded in uniaxial tension with a load in the x direction of 10 kilonewtons. What are the strains and deformations in the y and the z directions? The Young's modulus of aluminum is 70 gigapascal, and the Poisson's ratio is 0.33. This is the same example as we had in week 1, example 1. It's the same bar, but this time we're asked to find the strains and the deformations in the two other directions, in the y and the z directions. So we start by thinking about what Poisson's ratio is. So if I look at Poisson's ratio, we said in class that Poisson's ratio was the negative ratio of the strain in the lateral direction relative to the strain in the direction of the applied stress. So I could also write that the Poisson's ratio is equal to minus epsilon y over epsilon x, and it's also equal to minus epsilon z over epsilon x. So in week 1, we calculated the strain in the x direction. That's the strain in the direction of the applied stress in this case. And now we want to calculate epsilon y and epsilon z. So I'll say from week 1, example 1, we had that the strain in the x direction was equal to 4.76 times 10 to the minus 4. So therefore I can just write that epsilon y is going to equal epsilon z, and that's equal to minus the Poisson's ratio nu times epsilon x. So I get that by just rearranging this equation up here, and I can then write that that's equal to minus 0.33, the value of Poisson's ratio for aluminum, times my strain in the x direction, 4.76 times 10 to the minus 4, and that's equal to minus 1.57 times 10 to the minus 4. So that gives us the two strains in the y and the z directions. And then if we want to figure out the deformations, we can say that the deformation in the y direction is just the strain in the y direction times the original length in the y direction. So the strain is our minus 1.57 times 10 to the minus 4. And the original length in the y direction is the depth of the beam. That's the 20 millimeters. So we put down the 20 millimeters there. And if we calculate that, we get minus 3.14 times 10 to the minus 3 millimeters. So you can see that's a very, very small deformation. We can do a similar calculation for the deformation in the z direction. It's going to equal epsilon z times the original length in the z direction times the width of the beam. So that's minus 1.57 times 10 to the minus 4 for epsilon z. And then we multiply that times 15 millimeters, and that gives us minus 2.36 times 10 to the minus 3 millimeters. That's the end of example 1.